Hello, welcome. Decided to switch the face camera on today because I got out of the garage. If you've just been watching my PyOpenGL videos, you won't know what that is, but I filmed a couple of videos in a garage as a joke, and now I'm out. So, what we are going to do today is we're going to get multiple spheres working on the screen, and we're also going to start looking at some shading. It's not going to be perfect, but it'll be something. So first of all, you won't have to do this, but I'll just rename this and open it up. There we go. Okay, so what are we going to do? Well, first thing I'm going to do is I'm going to take the ray, just closing this all down. So to help out with this, I'm going to make a class to describe an interaction between a ray, like a collision between a ray and a sphere. Okay, so it pretty much is what it says. When the ray hits a sphere, we might want to remember all of that information that's associated with that collision. The reason for that is that we are now going to have a bunch of spheres, and the ray is going to go out into the scene and hit a bunch of these things, and we want to track the last hit because we want to know if the next hit is closer to the camera, basically. So this T is describing it's describing how far along the ray the hit occurred. Sorry, I'm just looking at this now. I'm wondering if we even need to store that, but it doesn't hurt. So now the next thing we'll do is if we go down to the engine. Okay, there's this hit sphere function, but none of it really uses the engine information. It's really just in there for convenience, so it might make more sense to put that into the sphere function, the sphere class. So we don't need that. But what we will do is we will update this a little bit. Right, you may see me looking over to the side a bit. I have notes, right? I prepare notes. I prepare notes so I'm not gimbling around like a goof trying to get this stuff to work. It takes many hours to troubleshoot all of this. So, what we're doing is we're running the ray and we are rejecting anything that's outside of a certain range. The reason for that is the maximum range will keep restricting as we hit more spheres. So we're going to be going closer and closer to the camera and rejecting everything else. Then we do the standard kind of solving code. We try to solve the quadratic equation for t. If we fail, then we try the other branch. Remember, the quadratic equation has two roots, two branches we can take on the square root, and then we just update everything pretty much. And also now we're returning a Boolean value whether or not the ray hit something. Good. Now another thing, if we go back to the scene, not the scene, sorry, the engine, where we go render scene. So what we've got is we've got this sort of stuff. We set up array, and then this is basically testing the code. So we want to take this and put it into its own function. The reason we want to put this into its own function is that as the ray travels around, it might bounce off things, and we want the function to be able to recursively call itself for, you know, bounces and things. So, just looking here. Yeah, let's grab all of this. What am I thinking? Of course, we can just copy that. So, we're just setting up a basic kind of okay, so we're going to set a few other things. We're going to keep track of the t value, which corresponded to the closest hit so far. And to start with, we're going to set it at a really large number. It doesn't matter. We're also going to track whether we actually hit anything in our scene. Okay, so we're going to accept anything down to 0 in terms of closeness. If we hit something, what do we do? Well, the first thing we do is we update the t value for the nearest hit. Yeah, sorry, we do need that t for render state. Okay, and the next thing we do is we flag that, yes, we did hit something. Okay. So this runs through all of the spheres. By the time that loop ends, it will have the color, the normal information, and everything for the closest sphere, the one that we should be rendering. So now we can go test. So I didn't think to check this before, but Numpy has a function where you can put in vectors and it element-wise multiplies them. It's called numpy.multiply. So what we want to do is we want to multiply the color of the last thing that we hit, and we want to multiply that with the sun color. Got it. So what does this do? Well, it shoots a ray and it does its little mathy thing, and then it gets a color. That color will either be the sun color if we didn't hit anything. I'm going to use the sun color as the background, in other words, white. Or if we did hit something, it will be the color of the thing that we hit. Okay, lit up according to the sun. So then we return that, and we'll use that here. So we'll go self.ray color, and that should work. So then I think let's just double check this set pixel. This looks a little dodgy. So we'll go break this out into its components. So this is just bearing in mind that now everything's going to be floating point between 0 and 1. And so what we're going to need to do is we're going to need to turn that into an integer. Alrighty, so this operation here is just a basic kind of min-max clamp. That'll just make sure that our values are within the right range. Then we just pass them in there. Okay, so always a good idea just to test this and check that it's working. And it is. But note that that took a while, and it's a bit annoying, especially like this video. The stuff we're doing is going to start to get more complicated, and it's going to take a long time. I was rendering just a second ago and it took like half an hour to render, so lucky for you, I'm going to speed this video up. But what we could also do, if this rendering takes too long, the program will think that our Python program has gone offline, and it will say not responding and it's not good. But we can make it print something. Actually, maybe not print every pixel, that's a bit much. Maybe every horizontal scan line. So we'll say, hey, does printing slow down the code a little bit? Not as much as the code's going to slow itself down anyway. So if you run this right now, there, we get our progress thing, and that is fine. Okay, so I'm just going to adjust this scene setup so that we can actually take advantage of having multiple lights. So we'll go to the okay, good. Hopefully that turns out fine. So this is just, we'll have like this last one's pretty big. That's going to be like the Earth that the spheres sit on. So just give it a second. And there we have it. Okay, so that's looking good. Right, so now the next thing is, notice around the edges of the spheres there's these jagged things. Let's do some anti-aliasing. Really, it's not as scary as it sounds. Basically, okay, so we shoot a number of pixels, not just one sample, but a number of samples for every single pixel. And let's say we shoot 16 rays for every single pixel. And they go ahead, they collect their information, they add it back into the color. Then in the end, we just divide the final color by 16, and that will take an average. So we're going to shoot 16 rays. That's my example. So now what we'll do is we'll set this up. We'll say color equals. Okay, so we're going to start with all zeros. Then we're going to do this a number of times. So we'll say we're, shooting the ray, adding it onto our final pixel color, and then we're going to draw that result. Okay, of course nothing's changing, so what we need to do is we need to add a bit of random variation. So we'll go numpy random uniform distribution, and this will just by default return something between 0 and 1, which is perfectly fine for us. So we're going to be off by at most 1 pixel in either direction. That's fine. Okay, that's looking good. So then we go to set pixel, and we divide this by sample count. Okay, this will take a while because it's slow. Okay, cool, we're back, and as you can see, we've completely given up on real-time rendering. That's okay. We're understanding the concepts of ray tracing. So hopefully you can see now the edges are smoothed out around the spheres. Of course, there's always going to be some jagged pixels because there's only so much we can do, especially just on 16 samples. But I've read that 16 samples is like the peak in terms of diminishing returns. Once you go above 16 sample anti-aliasing, we don't get as much. What I'm going to do is I'm just going to drop that down to 1, just because I don't want to slow my renderer down too much at the moment. So let's continue with the shading sort of stuff. So at the moment we're shooting shooting rays out from the camera, we're hitting spheres, and we're grabbing information. But what if we want a bit more information? So what really happens when a light ray hits an object? Well, it hits the object, then it rebounds. So what we're going to do is when we get an intersection in our ray color code, then we're going to recursively call ray color again to bounce the ray and hit something else. So let me just start this off. Okay. I know I'm doing such a good job of explaining it. So what we do is if we hit something, then yeah, we calculate this, but then what we'll do is we'll say update the ray's position to the intersection point, and then we need to choose a new direction for the ray. Okay. Then what we do after that is we will return okay, so just thinking. All right, so we do all of this, and then we recursively call ourselves again. So we set up the new direction for the ray, and then that ray bounces off, and we're going to collect the color from what that hits. And it continues and continues until either two spheres are right next to each other and it bounces around and goes down to 0, or it just bounces off and hits the sky, in which case it returns white, and then that will multiply back through the chain and we'll get the correct color, kind of. So then the question is, what do we do to get the ray direction? Well, this method is called Lambertian Spheres, and the way it works basically is we take the normal direction of the surface and then we pick another direction randomly and then add that to the normal. So we have the normal direction plus a random deflection. Because this is a matte surface, it is reflecting things randomly, not directed like a reflective surface would be. Okay, so what we'll do is we'll create a function to help us out, which will just give basically a random vector. Okay, cool. So this is just picking a vector with completely random components, and then we want to make sure that that vector with completely random components is constrained within a distance of 1 from the origin. So this returns just, if you imagine a unit sphere, just a point somewhere in that unit sphere. If this code is looking familiar, Raytracing in 1 Weekend is the source, inspiration for this series. I don't know what I'm adding to this. I am maybe putting my own spin on it, but essentially it's that, but in Python. So check that out. Really recommend that. I can't say that enough. Okay, so we've got that. That's good. So then we go down. Where was I? So what we do is we go render state. normal plus that random variation. And just to be sure, we will normalize that. Maybe not necessary, but why not? We can never go wrong normalizing things. Okay. Just double checking with my notes. Okay, that looks great. Except that we don't need to multiply by lighting them out again. That'll make things too dark. We've already done it over here in calculating color. Okay, good. So you can probably see the problem. If we have two spheres which are next to each other, then the light ray will bounce around indefinitely, potentially. So what we'll do is we'll also set up another parameter, which is maximum number of bounces, which we're going to let anything have. Let me just put it at a really low number right now, just to get this thing working. Okay. So we're also going to take the bounce index. I don't know, think that'll work. We just need to have an exit case basically, and the sun is white, and multiplying things with one is always safe, so that seems okay. Alright, so now what we'll do is when we recursively call this, we will say this is one more bounce, so increase the number of bounces, and when we initially run this, we will say start at bounce number 0. Yeah, and I'm gonna adjust that. Okay, that's fine. Okay, well let's run that right now and see what we get. Okay, that's interesting. So yeah, we're starting to see some things. As we can see, there's a bit of graininess, a bit of randomness, and I guess this is something we can work on. Interestingly, on the orange sphere, it's starting to get some bits of green. I have to imagine that is from rays kind of hitting the sphere, bouncing off, and deflecting down onto the green ground and reflecting that off. That's kind of cool, because it's kind of simulating the way light color is reflected by objects. And we got that for free, but we do have some problems. For one thing, we can absolutely increase the number of bounces to increase the quality, but we're going to hit a problem. So again, when rays get close and they bounce around a lot, it's possible that they will just keep bouncing too much. So if we go back to, where are we? Ray color. No. Yeah, okay, over here on the sphere.hit. So let's say that if the things are too close to each other, let's reject any hit which is closer than some margin. And that might help. Okay, cool. So there seems to be some improvement in the quality of the objects. Okay, so now, just to check that this thing is actually working properly, hey, I've got time. If you got time, I'm going to crank this up. I'll watch some YouTube, I'll crank it up, let's go for it. I'll make a coffee. Nice. So as you can see, we have that there. It's starting to look good. Geez, that looks better than I expected. We could even, I guess we could push the, I guess we could push the quality a bit more, but no, I'm happy with that. So, in the original source, Raytracing in One Weekend, they run this sort of scene with 100 anti-aliasing samples and 50 bounces, and it obviously looks better and actually runs faster because it runs in C++. But anyway, that's fun. That is it for today. In the next video, we're going to start looking at different surfaces, so like metal surfaces and glass surfaces and stuff. Hope you enjoyed watching. I had a lot of fun coding this up, and see you in the next one. Bye.